Okay, so today we'll first recap on what we finished last time, which is neural networks. And then we will talk about what is CNN, convolutional neural network. And we will go deeper about how we can use hyperparameter tuning and transfer learning to improve our models. We also dive into coding. So we will have a CNN collab where you would try to learn how to implement a convolutional neural network in PyTorch. And we'll end up with a workshop project talking about neural style transfer. You will learn more about it. So before we get started, we have I guess a opportunity for you to participate in some kind of AI development. So this is Vincent, and you'll talk more about it.
Hello, hi everyone. I'm Vincent. I'm a fourth-year undergrad. Was a former ACM AI event lead, and currently I'm very interested in large language models, specifically language agents, which put simply is using a language model kind of as a decision maker inside of an environment. And I've been working on this project for about 13 months now, and I'm in the process of sharing it with pretty much every club, every class at UCSD, every organization, and also other universities and research labs. So that's why I'm here. This is an open source research project where we aim to test as many language agent methods as possible across a diverse set of reasoning benchmarks. And the whole purpose of this is because these methods are very under-tested, and it's kind of hard to figure out what works best where and why. So that's kind of the question we seek to answer, and I'm looking for as much help as possible. And also thank you, Kevin, for allowing this to happen. Thank you.
All right, thank you. So if you would like to participate in this team kind of thing, we also post the poster after. So let's get started. First up, what is convolution? Convolution neural network by Rebecca.
Oh, okay, so last time we covered neural network, and then for that one, we didn't finish the collab. But for the collab, we also released the solution collab book. So we will highly recommend you if you want to review on how neural network works and how to write code for that. We highly recommend you to go to take a look at our ACM AI Discord and then look at the solution collab for that. Yeah. So for today, we will mainly be looking at convolutional neural network. So the first thing we will want to answer will be what is convolution. So convolution kind of means, if you know what convoluted means, it's kind of just looking at the same thing at multiple layers, at multiple levels. So basically remember what convolution means. And then for that, you will then have a better time understanding what convolutional neural network is. Okay. So here is an example of what convolutional neural network looks like. So it has been really used a lot or common for image classification because it's able to look at the same image multiple times at multiple levels. So here you can see that there are different convolutional layers. And then for each of the layers, it looks at the same image of the card at different levels so that it has a better understanding of what's within that image. Yeah. So there are three main components of a CNN. So what I mean by CNN is convolutional neural network. So it's a kind of neural network that we'll explore today. So the three main components, the first one is pooling, and the second one is activation function, and the third one is convolutional layer. So you can see the three of them in the diagram here. So here the conv is the convolution layer, and then the ReLU is the activation function, and then what's the last one? Yeah, and then the pooling is used here as marked in red. Okay, so we'll dive into the three of them one by one. Okay, so the first thing is pooling. So I guess pooling will be the easiest to understand concept for convolutional neural network. So the main idea of pooling is to reduce the information for a single image. So the main goal here is to reduce overfitting and have less data to process. And then since we have less data to process, that means less computing resource and then less money spent for like industry or like yourself with like the Google TPU. So what it does is that it tries to get an image is like overall like the general picture of an image by like reducing the like information from it. So here, okay, so there are two main types. Oh, I'll put it here. There are two main types of pooling. So the first one is max pooling, and the second one is average pooling. So for max pooling, what it does is it has like something called a kernel. So if you look on the right, this one is a max pooling. So it looks at them and then like within each kernel, within each area, for example, if you choose like 4 cells from this grid, you choose like the max of the cell with the max value, and then you then pick that one, and then for your output layer, you choose that as like the representation for that area. And then for average pooling, it's kind of yeah, so it's just like averaging that set of pixels. Yeah, so can anyone tell me like what would be like the difference between these kind of pooling? Like what's the difference in their output? Here you can see like one has like has more red like color, and then the other is like less intense. So yeah.
So I think the average tool would be like, it would give a better sense of like the overall like structure of the data you're inputting. Whereas the max pooling, it would give like a better sense of like the extremes of the data you're inputting.
Yes, that's really well put. So what's your name?
My name's Adi.
Adi?
Yeah.
Yeah, so what Adi just said is so for max pooling, you'll get a better sense of like the more extreme values within like your image. And then for average pooling, you get a greater sense of like what's like happening overall for like, that picture. So yeah, that's perfectly well put, because for like the more extreme values in that max pooling, you will choose that instead of like other ones. Yeah.
Take a picture with like not that much contrast. Would you want to use average versus max?
That
So if you have like a lot of light colored, I don't know, here, picture with a lot of like light pixels. You take the max, it's not going to mean much. So like, so would you rather use like average for that type of photo?
I think that depends on like what you want to do with that picture. So for example, let's say if you want to do edge detection, like find which the edge among like a image. I guess for using max pooling would be better, because you will then see like where is like the more intense values.
So like if it was classification, you want to use maybe average. Like if you wanted to say like this is a flower that with like a certain I don't know, certain type.
I'm not sure about that
So like
one.
you're saying object detection is good for max pooling or backwards?
I think you would be using both, right? Please, if anyone wants to like, is that correct? Is that correct with what I just said?
What was the question?
Like you will be using both of the pooling layers.
Both of the pooling layers, like both the max pooling and average pooling.
Yeah.
Usually usually people just use max pooling. I'm not really sure why, but seems like it's more effective. But for some cases, I guess like this is kind of like tuning your model, that you can try different stuff, and it's sometimes one does better than the other. Yeah, it's like a black box. Yeah.
So like, like, for example, like when you have a set of pixels, right? Like if there's like a lot of pixels and like the pixels are really small, like wouldn't max pooling like an average pooling essentially achieve the same thing, but average pooling would take longer? But then like if there's like very few pixels and they're all pretty large, then like average pooling, it would give like a significantly different result from the max pooling, right?
If let's say the image is like the pixels are very diverse, like maybe max pooling will be worse, because let's say your image is like for some pixel it's black, and then like right next to it it's like white or something, then we'll directly select the black one. And for average pooling we'll like get the average. So what you're saying is like it might be bad because max pooling will like ignore these white spots.
But so usually that doesn't really happen to most images because usually the images, like the context is pretty contiguous, like the pixel colors are pretty similar to the neighbors. So I think the main reason why people like to use max pooling over average pooling is because efficiency. Max pooling is much faster.
You skip pooling altogether, like if you have an image where you have really precise pixel data and you don't want it to be like, you don't want like pooling to mess with it, you just skip.
Yeah, you could, but then like the problem is the reason why we have convolutions is because well you through convolution you can directly only use convolution layers. That also works. People do that. The main point of pooling is to like how do I put it? I mean we'll be talking about receptive field later. And that will probably explain more of why you're trying like your question.
And for that one, if we have like, so the main purpose of pooling is also because we want to generalize like our learning with images. So, for example, if we don't do pooling, it might be, like the final classification result might be too dependent on like, the training data set. So maybe like the distributions are all like very bright images or something, or like one of them, there is like some part that's really bright. Then, maybe not all of them is like that, right? Then we want to make sure that the learning is generalized over all testing images, training images, so that in testing we can then achieve better performance. Yeah. Does that answer your question? Okay. Yeah. And then I guess this is like a small activity. So can anyone tell me like which one is max pooling and which one is average pooling? I guess the answer was covered previously.
I think left is max.
Like left was probably max and then right was average.
Yes. So this is because, so on the left one, you can see all of like the most prominent features, like the brightest colors, like the reddest red is being selected, over like for like the max pooling. And for the average pooling, you can see there's like a smoothing effect. So, you can see that on the right, like the brightest red is like being smooth because it was, the average with like the, other pixel values nearby. So for that one, we can like see like the overall look of what that image looks like. Yeah. Yeah, so you're correct. Yeah. So I guess this then brings us to like the other thing that we talked about. So for this one, we're given a really bright image of a cat. But do you really need this like 4K quality to identify that this is a cat? Okay, so the answer is probably no. So that's why we use the polling feature so that we can extract like we can use less like information to like identify it. And then the other thing is also because like for this one, you can see all of these are really short, like really sharp values. You can see that it's really bright. So we don't want our like classifier to be really dependent on like the things here, like the bright values here, or else it will be too dependent on these and then it will not have good classification result. Okay, so here's like a brief overview of what this cat looks like. If you use a average pooling and vs a max pooling. So here you can see for the average pooling image, it has like a blurring effect. So that's because we average all the values around it, and then we like so that all the values instead of like they have different pixel values, we average them and then replace all the previous values with the average values. So that's why there's like blurring. And then this is also what like blurring works in like real life context. You just average them so that it has like you get less and you have less information for like one specific image, but then you also save space. And on the most right one, that's a max pool image. So you can see it has a lot of like white feature. And that's because like white is like the most intense value within the image. So when you have like 255, 255, 255, that will be like a white color. So that's why when we have like a really big polling kernel, then it will be selecting all of like the most intense values. So then here it's like selecting all the white values and then replacing the cat with the white values. Yeah. Does that make sense so far? Okay. Yeah, and then here's a recap on like the activation functions we covered in our last workshop. So for activation functions, here's like different samples of activation functions. Essentially, what we want to do is it will be placed after each layer. For example, here we use ReLU to introduce nonlinearity for like the layer. So what we meant by that is we want to make the classification like harder. We want to avoid the machine learning model to feel like they have identified like a pattern already by adding complex nonlinear relationships into it. Because for neural networks, what they do is they add different weights plus like a bias, so that's like linear. So we don't want that to happen. So that's why we have activation function. And then here's like different examples of activation functions. So ReLU is like the most commonly used activation function. And the reason for that is because they just like try different kinds of activation functions. And then they looked at ReLU, and then ReLU has the best performance. So that's why it's like ReLU is being used right now because of like it's empirically achieving the best result for like machine learning models. And then here's like its variants, like leaky ReLU, LU. And then here's like softmax activation function. So for softmax activation function, it's used a lot in like I guess like digit classification or like different classification task. And this is because what it does is that it uses like the E, and then it takes a power by like the value of the each of the classes. So essentially what it does is that it maximizes, let's say that a value is really big, for example, 8 here. What we get here will be e to the power of 8. And then let's say the power, for this one, it's e to the power, this is 2. Then what we will get here is e to the power of 2. And then for the denominator, what it will be, so for example, for the case of the horse, so here's like different probabilities, like cat, dog, horse, like different scores. And then we want to convert them to probability. We will have e to the power 4 plus e to the power 2 plus e to the power 8 as the denominator. So that will be really, really big compared to 4 plus 2 plus 8, which is 14. So that essentially makes like, it converts a probability from all these scores into like the final value. So with what it achieves at the end is that it gives a more confident like result for like the probability of that image being within each of the classes. So here I think compared to like the values here, it's more like it's clear that it's like more likely to be a horse compared to like a cat or a dog, because here the probability is 0.98 according to softmax. Yeah. Okay. Is there any questions so far? Okay, it's clear. Okay. Okay, so the next thing is like the convolutional layer. So basically we have, so for the convolutional layer, we will have like a kernel that's like for example, for this one, it's a 3x3 matrix. And then essentially what you will be doing is you will be sliding it over for each of the like this image, and then you will get like a final value. So a key point for this one is that the kernel itself is learnable. So it's being learned through like the entire like classification process. So this is a bit of different from like what people usually do in the past. So what people do in the past is like they usually like hand engineer like the kernels that they will be using to get like the best feature extraction for the image. But then afterward, for a convolutional neural network, they introduce like learnable filters. So that right now is the machine learning model, like selecting the best kernel that they will be using instead of like human engineering itself. So this is one of like the intuition behind a lot of like machine learning models. It's like they want to create an end-to-end like framework, which the machine learning model choose what's the best value for themselves instead of like us human engineering for it. Yeah. Okay, so for a convolutional neural network, for each of the convolutional layer, there are some like engineering aspects. So these are called like hyperparameters. So we don't really know like what's the best value. Sometimes people have to find for it. So for the convolutional layer, this is like, there are three main hyperparameters for us to tweak. So the first one is the kernel size. And then the second one is the stride. And then the third one is the padding. So for what I meant by kernel size is like the size of this thing that we will be sliding over the image to filter through them and then select and then get like the final output. And for the stride, it is like by each of the step, how much will the kernel be stepping over the image? So for example, for this one, it's like sliding over it like one by one. It's sliding to the right one and then to the right one again. So for example, if you have the stride to be 2, then instead it will be moving through the image. It will be like hopping like 2 like each time. Yeah. And then there's also padding. So the reason for having padding is because sometimes we want to make sure that the image, like the final output, has like a consistent size. So sometimes people will be adding like 0 padding, or like they will be having no padding. Yeah. Okay, so for the convolutional neural network, one of the biggest insights for it, as Kevin has mentioned, is the receptive field being widened. So what I meant by that is by adding different kind of layers and then having convoluted views of the same image, we essentially want to try to widen the receptive field of the machine learning model for the image. So what I meant by that is for here, we want the machine learning model as when they see an image, we want them to see like the biggest overview of it. So what I meant by that is whenever we do like convolutional neural network, we always start from like big to really small details, and then we want the machine learning model to finally like for each of the layer, we want it to be like smaller and smaller, so that at the end it will be as small as like the final number of classes of what that we want to classify. So that will be, for example, like whether they are car, truck, airplane, ship, or horse. Yeah. And then all these are achieved through pooling, because for pooling, they will be trying to extract like the more general feature for each like image segment or area, so that they can see like a bigger picture from looking at like one area of the image. Okay, so here we provided like a fun example for a convolutional neural network. So the problem set up here is your friend just called you like tonight, and then they are like really sad because they just broke up with their ex-partner. So what they want you to do is they want you to give them comforting words, and what they will be providing is they will be providing everything their ex did, and then so essentially what you want to do is to be able to have all the details from your friends, and then be able to give like a more general overview of who their ex is, and then provide a good response to your friends. So here you're given what their ex did, and then you need to come up with words of comfort. And how you will be evaluated is by your friend's response. So whether they look happy when they hear what you said, or whether they look like unhappy. So here, yeah, so the overall task is to break down everything that X said and then generalize what they say to give like words of comfort to your friends. So the reason why this task is pretty hard is because we'll be given a lot of details, but you don't want to like just give comments on like these specific details. So instead, what you want to do is you want to be giving a more high level like judgments of that person. So that's why this is like hard. So this is where like a convolutional neural network might be helping you. So the training objective here is you want to give like the best words of comfort. And then your input data set is from your friends. And then your output is words of comfort. And can anyone give us like, what will be the evaluator?
Sponsor the friend.
Yeah. Yes. Okay, good. Yeah, so they will be the evaluator. Okay, so here's the input. So we are replacing the image of a car with the the description of your friend's ex, and then the output will be your words of comfort. So what would convolutional layer be in this case? So convolutional layer will be, you want to generalize like the details. So for example, if they say they are always late, instead of thinking about they are always late, you should be generalizing it to a higher level of like abstraction. So what you will instead want to see is that they were inconsiderate instead of they are always late. So that's like abstraction from CNN. And then the next thing is polling. So for polling, you only want to extract like the best feature. So for example, for max polling, when you're selecting, so different kind of polling will be different selection of the details. So for example, if you have max polling, you will be selecting the worst things their ex did. And for the average polling, you will be like trying to give out a general description from the description. So does that make sense so far? Okay. Yeah, so that is kind of how like you can apply CNN's concept into like real life situation, I guess. And so here are like the glossaries for like all the details of how it will be working behind the scene for anyone who's interested, if this helps. Yeah. And then here's our like other resources you can go over if you are really interested in like the technical aspects of CNNs. We'll be going over the Google Colab, but here are like a lot of like graduate course and then like CNN Playground for you to go over. Yeah. I highly recommend like this blog. Yeah, because this is from the famous CS231N, and then it includes all of like the technical aspects and like all the descriptions of how a CNN works. Okay, so then any questions so far? Oh, good. Okay. Okay, so next thing, so remember we talked about hyperparameter tuning. So for CNN's case, the hyperparameter to be tuned will be the kernel size, stride, and padding. So, but how do we actually do hyperparameter tuning? So that would be dependent on like how we want to tune our hyperparameter. So there are different kinds of hyperparameter tuning. So the first one, which is like the most primal way, I guess, will be to randomly select hyperparameters values by your gut feeling. Yeah, and then so that's called manual hyperparameter optimization. And then another one is you slowly increment through each of a value. So that's called grid search. So for example, you choose like 1, 3, 5, 7, 9, and then you try out all of them and see which one is the best. So that's called grid search. And then random search is you just randomly select values and then test them out. Yeah, so I guess these are all pretty easy, right? And then for course to find search, that's kind of like grid search, but then you refine like the step size for each of the grid. So for example, you can start from really great values like 100. So you try 0, 100, 200, 300, and then see which one has the highest value. And then you select the highest value, and then you decrease the step size. And then you do like 110, 120, 90, 80, something like that. And then see which one is like the best value. So that's called coarse defined search. And the last one is called Bayesian hyperparameter optimization. For that one, that's kind of involves a lot of technical concepts. So I will just provide like a resource for you here. So if you want to take a look at Bayesian optimization package, here's like one of an example for how you can be computing this. So if you're interested, take a look at how hyperparameter tuning is being done to this case. So this is like an even more like scientific or systematic way to do hyperparameter tuning. Yeah, feel free to take a look at that. Yeah, and then there's also a lot of like resource relevant to this that I will not be covering through like this workshop because of like time constraints. So there are like Google provided a deep learning tuning playbook. So for that one, they also included a lot of like other tips for you to like be doing hyperparameter tuning. So all of these will be really important, really helpful when you are like training your own models. Yeah. Okay, so apart from hyperparameter tuning, there's also another thing called transfer learning. So remember, all of us are using like large language models, and then each of them is being trained with like in a data center. So for us, we definitely do not have that money or like resource to be training all of these like machine learning models ourselves. So for a lot of like what researchers or what we can do right now is just to be doing something called transfer learning. So what we do with that is we take like the pre-existing model that big companies have been using, have trained like with their data center, and then we take that and then we only fine-tune part of their like layers. Yeah. So the benefits of that, the first thing is there's a lot less compute resources for you required to like do transfer learning and achieve greater results. This is because like other people have already trained them. You can just use that model. Yeah. And then there's also better performance because we ourselves don't have that access to resource and like GPUs. So it's better if we already use like something that's already knowledgeable, such as ChatGPT, and then we use something like that and then fine tune it and then do like transfer learning for other tasks. Yeah. Okay, so for transfer learning, there are two kinds of like transfer learning being applied to machine learning models. So the first one is the pre-train, something called the pre-train model that you will be doing for like classification or something. So for example, there's something there's a model that's being trained on something called ImageNet. So ImageNet is like a really large data set. So that model has already been trained with that. So it already has like previous knowledge or like ways of like how to classify different kinds of images. So what people do is they will get that model and they will like unfreeze the final few layers and then they will fine tune it with their own task or data set. So for that one, that's called using like pre-trained model. And then the other is to use feature extractor, using transfer learning on feature extractor. So yeah, so for feature extractor, they usually use like take models that have already been like released from other people. For example, the same one, such as the models being trained with ImageNet, and they use these as like image encoders to extract information from different kinds of data. So for that one, usually they don't do any fine tuning. They just use these models out of the box so that to get like their feature, like their ability of extracting image features from all kinds of images. Yeah, so these are two ways people use for transfer learning. Yeah. Any questions? I feel like this might sound kind of convoluted. Nothing? Good. Okay, so I guess an example of feature extractor to like that we can use for our own on our laptop will be, for example, if you input an image to, for example, ChatGPT, and then you ask like, what does it have in this image? And then ChatGPT will give you out like a series of descriptions of what this does. So with that, you are not tuning ChatGPT at all. You are just using ChatGPT. But for that, you are using ChatGPT as a feature extractor of your image. Yeah, does that make sense? Yeah, okay. Yeah, so here I included like something that would be good for you to know for when to fine-tune your model, but I don't feel like it would be. I think feel free to like reference this later when you're doing your own training, because I feel like it will be boring if I go over all of them. Yeah. So here are like all the resources that you can take a look at if you want to do transfer learning. So yeah, they will be really helpful for you, and then probably take like more than 20 hours to go through all of them. Yeah. So now it's collab time with our students.
So yeah, feel free to open the slides and follow this link to our collab for today. Yeah, and feel free to also make a copy. Oh, yeah, sure. I will leave it for like a few minutes. Okay, feel free to let me know if you still need the link, but otherwise we can proceed and look at this collab. Feel free to make a copy first. Let's do save a copy so we don't like mess up the original doc. Yeah. I want. Yeah. So we're gonna go over how to build a CNN with PyTorch from scratch. And it's gonna be like a very basic model, but something that you can begin experimenting with. So first we will start from like this start with loading the data set. Or do you want to say something? Oh yeah, sorry. Yeah, thank you. So we'll start from loading the data set and performing some transformations on it, like we did in our first workshop of AI School. So this one just translates the data to tensor format and then normalizes it. So the pixel values, instead of being from 0 to 1, they are now -1 to 1. If you are wondering why do we normalize it, it's usually a good technique when your values are like a specific range so that the model is trained more effectively. But honestly, I tried on this specific data set without the normalization, and the difference in like how good the model was like 1%. So you could try without it, or you can experiment with other transformations as well. So then we load our dataset. Our dataset is called CFAR, and it's very popular for learning how CNNs work. There's some notes for what those parameters mean in the comments as well. Feel free to also stop me and ask questions, by the way. First of all, when we do any type of work with data, we need to first understand how it looks like and learn some basic info about it. So that's what we're doing over here. We're just visualizing the data to understand like what we're working with. The first thing you want to know, how many classes are there for the images, and we print them with the first line, and we see there's like 10 classes of very like weird wide range with different pictures. And then we use matplotlib library to show those images. And this is how it looks like. If you try rerunning that cell, you will always see like different images in the data set, and some of them are very nice. Yeah. We can probably move on. Just let me know if you have questions about this. And now this is the most like interesting part where we implement our model actually, and this is what determines our model's architecture. So I don't know, my image is not here for some reason. Let me reload that. Is it there? Did I not? Yeah, I reloaded it. Let's see. Yeah, the image is not there. Unfortunately, I would just find it online right now. So um yeah, so I was looking. Can take a look at this image, for example. Oh, this one was a very good image. But this, oops, sorry. I have okay. Okay, that's technical difficulties. 1 second. How do you open it like, you know, big? Yeah, like that. That's what I wanted to do. Thank you. But yeah, this is like an illustration of kind of what we're trying to achieve. So we start from our normal image, and then we use a bunch of convolutional layers to kind of decrease the dimensions of that image and get like a flat layer of numbers. And then that flat layer of numbers will go through like a normal classical neural network that we talked about last workshop to actually determine which class it belongs to. So our goal is kind of, as you can see, our input is like a pretty complex image, and then we reduce the dimensions of that, and we just get like a bunch of numbers which correspond to probabilities of that image being of that class, which is pretty interesting, I think. So we start from, where's this one? So over here, we start with determining how many layers are there and how the model is going to look like. So as you can see, based on the comments, we start from first convolutional layer. And just those parameters mean, I think Rebecca mentioned what padding means. And then we see that we have 3 input channels and then 6 output channels. So this is represented by, in that image, this is kind of like, oh, wait 1 second. So yeah, so this little yellow box is what's called kernel, and the dimensions of the kernel are also one of the parameters you're allowed to choose for your convolutional layer. And then and kind of it also determines the dimensions of how your output is going to look like. So in addition to those layers that we just added, so after, like, let's say 2 convolutional layers, when we reduce the dimensions of our image enough for it to go through like linear normal layers, as I showed you on the image, we have those linear layers. And then the last layer, this is what produces our output, which is like the probabilities. The reason why like this is just for clarification, the first one over here, the first parameter, is your input channels. So basically how many numbers, how many dimensions of input are coming into that layer. And the second one would be how many dimensions are coming out of that layer. So on the image, let's say for a fully connected layer, when we have linear layers, you see that like one layer, like the light blue dots is the number of input dimensions, and like the less light blue dots afterwards are your output dimensions. Yeah. So let's do that one. Yeah. And in addition to that, we for the forward propagation, the reason we called it like that is this is when we take our input and go forward through that chain of things to get the output. This would be like our forward pass. And then after that, we will calculate the loss as usual, and then we will do the back propagation to update the parameters. And that's why this is called forward. And here we define also our activation function, which is ReLU. So basically what that line means is that after convolutional layer 1, apply ReLU function and then do the max pooling technique that we talked about to reduce the dimensions. Yeah. And this, by the way, like for max pooling, the second parameter means by how much are we reducing the dimensions of that image. Yeah, flatten means that for something that has multiple dimensions, like I say, 2D array, 3D array, flatten just means go from those multiple dimensions to single dimension. Yeah. Because convolutional layers work with multiple dimensions, like multi-dimensional data, and to put it, our results, to put it through linear in the end and produce linear output, we need to make it linear at some point to be able to go for like this fully connected part that's in the end. Do you have any questions so far? Maybe? Okay, just let me know if you do. Yeah, so when we defined kind of this model, just by the way, the choice for architecture of like how many nodes are there, how many, like what dimension is the output and how many convolution layers are there and how many linear layers are there. This is kind of a choice that was made here arbitrarily without like any specific thought. And that's something that you can experiment on to try and change, like make like better predictions in the future. So those are like up to change and you can experiment with those. Next, when we define how our model looks like, we want to train it on the data set that we just loaded. So we define the loss function. So that's the thing that we want to minimize that will determine how much error is there. And this is the function that we want to minimize. Yeah. We're using Adam optimizer. We talked about gradient descent last workshop. Adam is like a pretty sophisticated, more complex version of that, but I did include a link like above if you want to read more about Adam. And there are also other optimizers that you can also experiment with. So after we define that, we have our training loop where we go through all the data that we have and then like forward. And then we optimize, like calculate our loss. And then we go backwards, optimizing our parameters. And yeah, just to remind, epoch is the number of times all the data goes through the model and how many times like the parameters are optimized. Yeah. And in the end, while you train this model, I also did like the print statements to see how loss looks like after each epoch. So after every run of like the full data set through the model, how the loss function is looking like. So we see like the first epoch, the loss is kind of pretty big, and then by the end of it, we optimize our loss function and it becomes way smaller. And this is like the training part is usually what takes a lot of time. So if you were to create like a very complex model with a lot of layers or maybe with a lot of epochs, so a lot of runs for the same data set, this would take longer and longer time depending on how complex your model is. And then, yeah, since we trained the model, we can look at how it predicts things. Let's do an individual prediction on like an example. So here I arbitrarily chose an image number 9 in my data set. And then, yeah. You can try like, if you ran the code yourself as well, you can try changing this to see different images and predictions for those images. To make a prediction, we need to switch the model into the evaluation mode, which means that we stopped the training process and now we want our model to start predicting based on like an example. So we don't want like any backpropagation, we don't want to update any parameters anymore. We just want to start predicting based on the model we just trained. And then we can showcase how the prediction is looking like. So the actual label was automobile, that's how the image is looking like. And then the predicted label is automobile. I think there was like a funny one that I don't understand what means. I will show you. I think it was 0. Oh yeah, I will have to rerun the whole thing, huh? But yeah, just it's pretty interesting. Try changing this index of the image in the set, and you will see like different images and what it predicts that image to be. And then to evaluate the model, we're basically doing this like individual prediction process, but on everything in the test data set. And then we count how many were guessed correctly and how many there are total things. And that's what gives us the accuracy. And the accuracy of this model that I just showed you was 64.6. Yeah, which is not too awful, but also not good, I would say. So now I feel like it would be very interesting for you to try and use the manual hypertuning approach and try changing a few things about the model if you could maybe beat the 64.6 over here. And there are a bunch of different ways you could do that, which are changing the model architecture, as I mentioned, like adding more layers or changing how many nodes are there, or like the kernel size when you do the convolutional layers. There is also data augmentation method that basically you're working with your data in order to create more artificial samples. And by that, I mean you could take one image, you could flip it around or crop it or rotate it or change the saturation of it. And by that, you will artificially create much more samples out of only one single image. And that what's called a data augmentation. Then optimization and regularization techniques. There are different optimizers. Atom is pretty good. There are also other ones that you can also look into if you're interested in that. There are also dropout layers, which are helpful when you see when you program is overfitting. And by overfitting, I mean is when you train your model on a training data set, sometimes the model will get used to that training data set so much, like it will adjust weights that it predicts the training data set pretty well. But when you go out in the world and actually try different examples, you will see that accuracy on like test set drops significantly. That means that the model was overfit on that training data set and only good at predicting the training data set that we don't want. So dropout layers allows us to skip some of that, to skip this process of getting a little too close to the right like training value, so that our model is like more robust and can produce like and can adjust to like a wider range of features kind of. Then hyperparameter tuning is what we mentioned. If you have a hyperparameter like learning rate or batch size, I will clarify that in a bit, or number of epoch, we can also try and change that. So learning rate is basically just how fast your model is learning. Or if you remember last workshop, we did like the gradient descent, and I showed like a picture of like how you start at a certain parameter, and then the purpose of gradient descent is just to like go down to like to the parameter that minimizes the loss function. And learning rate is how fast you're like moving in that plane. So if you're moving too fast, you'll kind of like just randomly move in like different directions, which is too far steps. If it's too slow, it will take too much time. If your step is too small, it will take too much time to get to that minimum value. So that's why you need to like choose something in the middle. Batch size is how much of the samples your model is loading at a time. For this model, it was 32 at a time. Then epoch, I mentioned that before. That is the number of like full passes that your model is experiencing. More epoch usually means better accuracy, but also each epoch takes time, so we don't want to take it too long. There's also like transfer learning, as Rebecca mentioned. So if you don't want to wait for your model to train for too long, you can always use some pre-trained models as well. And yeah, there's a lot of other techniques probably that I didn't even mention right now. So yeah, I would like to give you some time, maybe like 10 minutes or so, to just look at the code like that I showed you right now and try changing a few things about it to maybe achieve like a better result than this. Yeah, just be sure to not like make your model too complex, because it will take a long time in that case. Yeah, and we will be around. Please let us know if you have any questions.
Oh, not right now, just right in front. When you would you?
Yeah.
Okay, hello. Yeah, so I think that's a decent amount of time. Hopefully, you guys made some progress and we're able to understand a bit more. The next thing we're going to be getting into is probably not as important for your general AI knowledge, but it's just a little bit more fun. Do I have to? Oh, yeah. Yeah. So this next part is just a bit more fun. We're gonna be doing neural style transfer. This is not like something that you learn super often because it's really kind of uh it's mostly cool. That's what it is. So basically what it is we have this picture here of these houses, and then there's this painting. It's a pretty famous painting. It's called The Scream. And we kind of put these two images into the machine, and we get like a mix of the two. So it's kind of like the houses with like the Scream style. So it's style transfer. So we kind of texture the image using our style image. So I think that's pretty cool. So we're gonna learn how one does this. So I'm gonna go into the theory mostly, and then there's a collab at the end, but we don't have too much time, and it's just like a few short code blocks that you guys are gonna do. So you guys can do it now if you have some time at the end. But otherwise, I'm just gonna give you guys a solution, and you guys can try implementing it yourself after, and I'll just explain the theory and stuff now. And then you can check like what you've done according to the solutions. So the way we do this is uh, there's many steps. It's a bit different than what you've done so far. Uh, but the first step is selecting a pre-trained CNN for feature extraction. So the reason we want a pre-trained CNN is because we want something that is already has learned how to, find certain features, can do object detection fairly well. So we take generally some sort of large pre-trained CNN like VGG19. Or like a similar deep network, and it can capture like certain features. So you have both your content features, so if there's like a face, or like the houses we just saw, like the actual outline of the houses, the windows, the roofs, the shape and all of that. And then we also have the style, which is like the painting we saw, maybe the certain color, the palette that's being used, maybe the sort of like brush strokes, how thick it is, all of that. um so you've just learned a lot about CNNs. So the higher layers of the CNN, they kind of capture like those outlines and things like that from the content image. And then for the style, we kind of use both the higher and the lower layers for like the textures, so the different colors, the you know textures. But yeah, that's the first step, is taking a pre-trained CNN. And then basically we have three images here. So like I mentioned, the content image, which was the picture of the houses that I just showed you over here. And then the screen here would be the style image. And then there's a third image, which is the generated image. There might be some different names for the generated image. It could be like, some people call it like the combination image. So the combination image is uh, it's not like anything specific in the beginning. It's just an image. It can be a completely random image. It can just be like noise. It can just be a copy of the initial content image. But the point is, this is what we're going to be generating. So our goal is to generate the kind of mixed image at the end, the content image with the style on top of it. So those are three images that we need to know. Then we start by passing the content and the style image through the pre-trained CNN. And what we do when we pass it through the pre-trained CNN is we freeze the parameters. So the reason we do that is because we want the CNN to pick up on the features in these images. So usually we kind of have like, the model, the data, and then we like put the data through the model, and then we see like how different it is from like the desired output that we want, and then we kind of change the model a little bit. We like change the weights and biases, and then we run it again, and then we keep running it over and over again until we get like a really cool, really great working model. But here we don't want to do that. We like our model already. This model is pre-trained. It's pre-trained on a lot of great data, and it's working already. So what we want to do here is instead of changing the model itself, we want to change the images. So if we were to run the content and style images through the CNN, and we did the same thing like how we've done in the past, where we changed the weights and biases, then the model will be like kind of too biased towards these. It kind of like change what we want and like spoil the qualities that our model has already, which is it's really good at picking up on features and styles. So we pass it through so that it remembers, it extracts certain features from the content image and the style image, and it saves that. And then after this, we don't have to even use our content image or style image ever again. It just kind of saves it and it keeps it with it. So like I said, for the content, we use kind of the higher levels for the outlines. And then for the style, we use the lower and higher levels. Yeah. Then we also want to define the content and style loss functions. So what's going to happen is we're going to run this generated image through the model, and it's going to kind of calculate how far it is from the content and the style images that we had before. So for us to do that, we have to figure out a way to calculate like the loss for each of those things. So especially with images, we have to like have very unique things for both of these. So because like there is a significant difference between the content and style that we want. Like we still want the houses to be there in our final image, but we don't want, the scream face to be there. We just want like the coloring of it. So there's a different loss function for both the content and the style. We can't just kind of like add them together and then average it out, if you know what I mean. Also, feel free to ask any questions if you have any. So the content measures the difference between the features and then the generated image in that specific layer. And then that's how we figure out the content loss. The style loss is a little bit more complicated because it has, like, it's not just outlines, it's, many different things. We have to we want to pick up on patterns in the style image. So it uses something called a gram matrix. So a gram matrix basically figures out the correlations between feature maps, and then it kind of encodes the textures and patterns. So a feature map, I should probably also define what a feature map is. When you run that original content image and style image through the network, it picks up on features and it creates feature maps for each of these things. For the style loss, you don't just have a feature map. You also want to figure out like the correlation between the different features, right? Because when you're thinking of something like style, you want to understand like the pattern that's there. It's not about the specifics, it's about the pattern that emerges. So, you see like we're using blue and yellow a lot together. So maybe this is something that, our generated image should have this kind of an impression of the style that we have. Maybe around the outlines, it's a bit softer. Maybe that's something you want to pick up. And you kind of like put two and two, and then you just kind of build some sort of pattern out of that. So that's how the style loss works. And these are the specific like formulas to calculate the content and style loss. This is MSE stands for mean squared error, if wasn't clear. Yeah. Then we define the total loss and optimization. So the total loss is what we're trying to minimize. So as the more we minimize total loss, the more we kind of get to this ideal final image that we're looking for. And since content loss and style loss, like the final output could be on like orders of magnitude different, we have to put some sort of weightage on it. So that's what the alpha and beta here are. So the total loss is alpha into content loss plus beta into style loss. Alternatively, you could also just do like just beta into style loss because just kind of put it on the same level. And using the weights, you can either put more emphasis on style or you could put less emphasis on style. I'll show you later why that could be helpful when I actually go into the final example. But yeah, that's what we use the weightings for. The weighting can be anything that you want it to be. Generally we use something like fairly standard. Yeah, so the objective is to minimize that total loss that's there by adjusting only the pixels in generated image. So like I said, instead of changing the model, we're then running our generated image through it, and we're changing the generated image. So instead of the model, we're changing the image itself based on the model. So we just changed like individual pixels in our model. And then this is the final step, we optimize. So again, instead of updating the CNN's parameters, we update the pixels in generated image to reduce the total loss. And then we kind of run back propagation on that again. So we keep running it through over and over again until we have like a really nice final image. So then over many, many iterations, you know, it can be as many as you want. The code that has been given to you is about, I think, 1,500 iterations. It eventually, the generated image, which is just a random image, takes on the content, the structure of the content image, and the style of the style image. Okay, so that's the steps. I know that I just want you guys to kind of understand on a high level, but are there any questions at all? Okay, so, I think instead of implementing everything right now, I just want to show you what it looks like. I'll kind of run through the final solution code, and then you guys can give it a shot yourselves after. And then we can also just talk about, we can also just run through a couple of examples of your choice. So that part will just be fun. That's just chill. You guys can pick what images we want to do. But yeah, so I just want to explain the overall structure of the code. You guys can just go back to the original collab that we were in. I can just keep the uh, link up a second longer. Yeah. Okay. Everybody good? Okay. Oh, we're on the CNN right now. Huh? Sorry. Okay. Awesome. So here's just some of our imports. I'll show you the stuff that you guys actually have to implement. The reason that there's so much like code already given to you and you guys only have to implement a little bit is because a lot of the code is not really machine learning related, it's just kind of um, displaying and like inputting things. So you guys will just have to implement the content and style loss. So the first example we're going to be doing is with Barack Obama, but I'll show you guys that right after this. Here's the content loss class. This is the part that you guys are going to have to implement. And that includes, uh, having to detach from the target to avoid like computing gradients, which would change the model. I also, okay, wait, that's later on. Okay. And the gram matrix is already given to you because I haven't gone super detailed into that. The style loss, you guys will have to implement that as well. Importing the pre-trained model, like I said, you can technically do whichever pre-trained model you want, but the very common one is VGG19. That's I think the latest one. I've also seen VGG16 a lot, so I'm not fully sure. The normalization you guys don't have to do. Then you kind of just have to implement the final running of the style transfer. That's just one function, and then that also includes the optimization as well. And the only parts of this that you'll have to implement is kind of just tallying up the style and content losses, putting the weights, calculating the final loss, and the code will just do the rest of it for you. But I think my main goal with this is not for you to implement the entire thing, but it's just to kind of understand the high level. So, you can experiment more with this code, whatever you want later. And we'll do some experimentation now as well. So yeah. I just have this because this has the completed code right now. So we can actually try it out. Like I said, I started with like a picture of just like Obama. So I'm gonna take a picture of Obama. Spelled it wrong. Okay. Maybe just like the Wikipedia one, if that. How do you right click on Max? Yeah, how do you? I don't know. How do you save this image?
You want this copy image out?
No, just I want to save it. Yeah, that's good. It's a JPEG, right?
I hope.
Yeah, it's JPEG. Yeah, cool. Wait, so what do you do to get the right click?
Two fingers.
Oh, okay. There we go. Okay, and then I wanna do a Picasso because I like Picasso a lot. And this is I think the image I want to use. 2 clicks. Okay, cool. Um, let's just make it cubism. Okay, awesome. So I've already added this stuff. I need to upload it here. How do you do this? Shift. So and my content image will be the picture of President Obama, and then the style image will be this cubism painting by Picasso. Okay, we'll just open that. Okay, so so now I've uploaded these two JPEGs to my Colab, and over here, there's the line for the style file. So I put cubism.jpg and President Barack Obama.jpg. So now we can run everything and we can kind of see how it works out. And then after that, I'll let you guys decide one for us to do. Like I'll just take 2 images from you guys and then we'll run that and then you guys can implement it yourselves or you'll be free to leave as well. So let's just do run all because I just want to run everything. Hopefully it works. This might take a while. So okay, it's not bad. So this is the style image that we're going to be using, and this is the content image that we're going to be using. So expect this as that style. Okay, awesome. So we just kind of showed the input image again. And then this is the style transfer thing that you'll be implementing. And yeah, okay, so now it started running. So we can, like I said, there's 1,500 iterations. And we'll get to see, I think, every 50 iterations, how the image changes. Okay, cool. So this is it at 50, so it's kind of changed a little bit. Yeah, I think that's pretty good. Okay. This model is actually quite fast, so already at 50. Yeah. So I think actually I'm preferring some of the earlier iterations of this Obama picture because I think it's kind of like his features are getting a bit more dull as we're going along. But let's just wait for it to finish. I think just do more. Yeah. Okay. I think that's it. This is the final styled output. Whoa. Okay. So that's what it looks like. I think it actually looks cooler when you zoom it in and kind of see all these other details that are done. It looks pretty cool. It kind of looks like a Pablo Picasso image of Obama. But yeah, yeah. So I think this is what I said that will come into relevance later is that sometimes I think in this case, since it's kind of blurred out a bit, maybe one of the earlier iterations would look a bit better because it has more of its features clearly. Sometimes we may have weighted style a bit too much here, so it's kind of like drowned out the content. So maybe if we had weighted content a bit more, style a bit less, then the outlines would be more clear and then we'd get slightly better of an image. But I still think this is a pretty good job. Yeah. So I think we have 10 minutes. Does anyone want to suggest another image for them to do? Just like either a style image or a content image. Um, yeah,
Starry night, just like really cool.
Cool.
Style. I don't know what.
okay. And any content image? Oh, okay. I like that. I like that. Okay. I hope. Okay. Oh, let's just do starry. There we go. Better. And we said Lightning McQueen. Which picture of Lightning McQueen do we want? This one? Middle one?
The one where he's on the race, go down.
This one?
Yeah.
Okay, awesome. Okay, cool. Let's just do McQueen. So that's easier for us to type it. Okay. 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 So those who have loaded in our style file, we will put starry, and then the content, we will put McQueen. Okay, awesome. We'll just run everything again. Okay, so again, style image, content image. I'm very curious about how this will be. Maybe, I don't know if the conflicting colors will do anything, but hopefully it works out for the best. Yeah. I used VGG 19 for this. I've read some sources online that an older model might actually run a bit faster, but I don't know if that's necessarily super true or not. But maybe a more updated model will get your content features better, but I don't know. Okay, but we've also like resized them because they have to be compatible with the images. And I've also made them like a bit less like HD or just kind of normalized it a bit. Okay. Ooh. Okay. That kind of like,
Yeah.
yeah. This is what I call art. Oh yeah, the audience has kind of become like the stars. Okay, that's actually a lot better than what I thought it would be. Okay, it's almost done. Okay. And that's the last one. Yeah, there we go. I think that's pretty good. That's actually better than the Obama one. You can still see his features. Nice suggestion, both of you. And yeah, I think that's all for now. I'll be sending the solutions to all of you guys later. And yeah, hopefully you guys have some fun trying to implement this, and then, and maybe send any cool outputs that you guys get, any cool examples that you guys have. And yeah, I think that's pretty much it. Kevin, you want to say anything at that ending? Or?
Yeah, I guess, thank you for coming to the workshop. We'll have the last one, on week 9, so in 2 weeks again. And also in this room, and that workshop will be covering, more like real-time real-time image classification, or like real-time, style transfer also works. And then, trying to deploy onto like a web application is something we want to do. So yeah, so if you're interested, please come to the next workshop, to like finish up with the AI school. Yeah. And last one, if you have any questions, like when you're trying to work on maybe the CNN collab or the neural style transfer collab, you can always ask inside of the Discord. And the solutions and the recording should be released in a few days. Cool. Yeah. Thanks for coming.
Yeah.